Good afternoon, everyone. Now it's time to look at equilibrium, more specifically static equilibrium. In physics, equilibrium has a very specific meaning. It is when the object is not accelerating linearly or rotationally. That's it. An object is in equilibrium if it's not accelerating linearly, which means that the net force, or the sum of all the forces acting on the object, is zero. It's the only way it cannot accelerate. And if the sum of the torques acting on the object, or the net torque, is zero, that's the only way it will not accelerate angularly. We have two types of equilibrium. We have static equilibrium. For example, this board is in static equilibrium. The sum of the forces acting on it is zero. It's not accelerating to the left, right, up or down, front or back. The sum of the torques acting on it is also zero. It's not tilting this way, or that way, or this way. This marker is in equilibrium. Now, I am in equilibrium. The two cases of equilibrium are static equilibrium or dynamic equilibrium. For example, if this ball moves at a constant speed that is not zero, it is in dynamic equilibrium. The sum of the forces is zero. It's not accelerating, constant speed. I should even say constant velocity. And the sum of the torques acting on it is also zero. It's not accelerating or rolling. You're going to have an object that rotates on an axis at a constant angular speed. That would be also an object in dynamic equilibrium. For our purposes, we'll focus only on objects in static equilibrium. The sum of the forces and the sum of the torques is zero, but also where the linear velocity and the angular velocity are zero. In a situation, what we will have to first do is draw not just a free body diagram, so assuming that the object is very small and all the forces act on the same point, but draw the extended body. Usually it will be symbolized by a rod or a rectangle like I had in the previous diagram. And we'll need to draw where the forces act on this object, but we'll need to determine also where the pivot point is. For example, if I have this marker that is at an angle, I'm holding it here, and we can draw the forces acting on it. It is presently in static equilibrium. This is a bad example. Let's actually use another example. My arm here. I say this example in the notes. Right now, I'm holding my arm upright, well, horizontal. I do that by engaging the deltoid muscles and other muscles in my back and neck and everything else that I forget because I have not done biology in a while. But if I let go of all muscle tension that I have, this happens. My arm falls down. So what we can do is draw the forces acting on my arm at this moment. I can even do one better and have a mass in my hand. So this is what I'm doing. I am holding upright a ball, and let's analyze. I have is my arm that will make an analog to a rod. I will ignore the fact that it can bend. I will consider it to be rigid. What we have is a fulcrum at my shoulder. We have a ball. We have the mass of my arm. We have muscle forces here. Let's draw this. What we'll do in most cases, if not all of the cases that we have, is consider the forces only to be acting in the x and y direction, which means that all of the torques will be in the plus or minus z direction by the cross. This is symbolized by this positive rotation, determining the counterclockwise direction to be positive rotation. And these are the forces that we have acting on my arm. We have the normal force from the ball because I am holding it upright. There's a gravitational force of my arm because it's always there. We have the tension in the deltoid muscle over here, and it pulls some distance away from the shoulder. It pulls at some angle that is not 90 degrees. It's not perfectly perpendicular, or it's not perfectly along the y direction, and it's not perfectly along the x direction, positive or negative. If you notice, we need to balance things out by something that I call big R, the reaction force. And that is something that appears often at the fulcrum of the situation. This reaction force can be many different things. It can be the normal, it could be a friction force, it could be a combination of the two in 2 dimensions. It could, in the case of my shoulder, it's the force that's happening in between all of the bones inside the shoulder joint. It would be the same thing if we were considering the elbow or the hip or anything else. The next thing we must do is determine where all those forces act with respect to the pivot point, considering that this is, for example, 0, 0, exactly at the origin. We'll have some distance in green, RT, that we can determine or would be given to it. We have a distance in red, RG, and we have a distance in blue, RB, for the ball. The distance from the reaction force is 0 because it acts exactly at the fulcrum. We then need to determine what the angle is in between the green vectors and the red vectors and the blue vectors. For the red and blue vectors, in both cases, the angle is 90 degrees. The forces are perfectly vertical, and I'm holding my arm horizontally, which means that these position vectors, RG and RB, are perfectly horizontal. We need to then determine the angle theta t here in green, and the angle theta r in black. Once we have done those things, we can write what Newton's second law is in the x direction, what it is in the y direction, and what it is in the z direction, or for the torques. In the x direction, we would have a plus sign in front of the component for the reaction force. It goes with the positive x-axis, and minus t deltoid x, and all of that is equal to 0. In y, we would have positive components of r in y and of t deltoid in y, and negative components to fg and n ball, or all of them really, because they're perfectly along the negative y direction. All of that is equal to 0. And then we write the sum of torques. And that would be the torque of the deltoid. If I'm only contracting my deltoid muscle here, assuming that it's the only muscle that's acting on my arm goes up, counterclockwise rotation, positive torque. If I only consider the gravitational force on my arm, the arm goes down, negative rotation, negative torque. If I only consider the force of the ball, arm goes down, negative rotation, negative torque. The sum of these three is still 0. And then what we would need to do is use the definition of the torque, of the magnitudes of the torque, Rf sine theta, or sine phi, with the respective angle, the respective forces, plug in here, and then once we have done that, we've done the physics of the problem. The rest is just algebra to solve. But essentially, this is static equilibrium. It is a very complete thing that involves everything in dynamics, Newton's second law in linear motion, rotational motion, and can be algebra intensive, but it's nothing you cannot handle. So I believe in you, go practice, and I'll see you in the next one.